So one side's already equal to 0 in this equation, so we don't need to worry as much about that first step we had last time. We just want to factor this thing out, because there's really no way to get these x's by themselves. There's just way too many of them, right? How you can get that x by itself? The only thing to do is factor. So I'm going to break this up into two pieces, like so, and look at each piece separately. That first group, I noticed the largest thing that goes into 4 and 12 is 4. And of course I can take an x squared out of both of these guys. And what would be left behind if I took 4x squared away from here? I'd have just an x, and from the negative 12x squared, I took the x squared away. I'm dividing it by 4, so I have negative 3 left. If this is still giving you trouble, think about what would happen if you took 4x squared times x and 4x squared times negative 3, and you'd see you have this thing staring you back in the face. So we're just basically doing a reverse distributive property. For this second grouping, it does start with a negative number, so I'm going to at the very least pull out negative 1, but in fact the 9 and the 27 also have a 3 in common, so I'll pull out a negative 3. And what's left? Well, I would need to get a negative 9x. I have a negative 3, so if I multiply this by a positive 3x, that would give me the negative 9x back. If I wanted to get a positive 27 with a negative 3, oh, my goodness gracious, that's not the GCF at all. There's something that's bigger that goes into 9 and 27, and that would be 9, wouldn't it? So let's pull a negative 9 out of here. And then I would say if I pull a negative 9 out of here, all that's left is an x, and all that's left from the 27 is a negative 3. That's all equal to 0. These are identical. They weren't about to be, which is why I paused and freaked out for a second. Now they're identical. Great. So that's a common factor. I can put that out in front. And what's left behind? If I took this guy's x minus 3 away, I still have 4x squared. If I take this guy's x minus 3 away, I still have negative 9 equal to 0. And we're going to set each part equal to 0. So this means either x minus 3 is 0, or this crazy quadratic from chapter 2 equals 0. Standard 2.2, I think. Solving this function gives us x equals 3, equation. And here, maybe you notice that this factors quickly because you see these are perfect squares and they're subtracted. So you know this breaks up into 2x minus 3 times 2x plus 3 equal to 0, because these will multiply to make 4x squared. These multiply to make negative 9, and the inner and the outer make 0. And from there you can find 2x minus 3 equals 0, which means 2x equals 3, which means x equals 3 over 2. 2x plus 3 equals 0. And following similar steps, we get x equals negative 3 halves. Or if that does not make a ton of sense to you, or if that's not ringing any bells, option B is to say we have 4x squared minus 9 equals 0. There's just a single little x squared there, so I can get that by itself by adding 9 to both sides of the equation, dividing both sides by 4. And when I square root both sides, I got to put in that plus or minus. The square root of 9 is 3, the square root of 4 is 2. But any way you slice it, our final answer is going to be x equals 3, or plus or minus 3 halves. I went a little fast with this last bit of things, It's a lot of stuff from section 2.2, and it all depends if you prefer solving something like this by factoring or by isolating x squared and square rooting.